Hey everyone, in this video we're going to do two examples where we're asked to find the governing equations in matrix form, but we're going to do the first one by using the free body diagram method, and then we're going to do a more complicated system, or slightly more complicated system, with the direct method. And this is just to show you how much time it saves you, and basically that it works. So the way that we do this is that we will draw a free body diagram for all the degrees of freedom. And the way that I figure out how many degrees of freedom is that I ask myself how many fingers would I have to put on the system to stop it from moving completely. Now, in the first case, it's pretty simple because if I put a finger on this mass over here and this mass over here, then it's completely frozen. So I will choose these two to be my degrees of freedom. I'll call it x1 and x2. Alright, so let's draw a free body diagram for the first mass. The way that I draw the free body diagrams is that I tell myself, alright, well, since I'm doing the first mass, imagine that the second mass is totally constrained, it can't move, and then take the first mass, the free one, and move it in the positive direction, so in this direction, and then in this direction for the second one. If I do that, I will expect a force on the left side from the first spring, and also from the first damper, a force to the left from K sub 2 and C sub 2. Fk1 is equal to Kx1, Fc1 is equal to Cx dot 1, because the damping force is equal, or rather proportional, to the velocity. Fk2 is equal to K times x2 minus x1, or rather x1 minus x2. Fc2 is the same, but with velocities. Alright, and then we apply Newton's law and say that the mass times the acceleration is equal to the sum of the force. In this case, it's Kx1 plus Cx dot sub 1 I'm going to group like terms. So I'm going to get K plus K x1 plus minus K x2 plus C x dot sub 1 plus minus C sub 2. That's pretty easy. Alright, let's do the same thing for the second mass. This is mass 1. Alright, number 2. Write out what it is right off the bat. We're going to Fk2, Fc2, 3 FC3. Okay, so fk2 is equal to k x2 minus x1 fc2 c x dot sub 2 minus x dot sub 1 fk3 is equal to k x2 fc3 is equal to c, or 2c, yeah, x dot sub 2. And so Newton's law again, group-like terms. Alright. Now, one thing that I forgot to write is that we need to take all of this and multiply it by minus 1. All of this multiplied by minus 1, because they're all acting to the left. The mistake that I did here is that I assumed that they were all acting to the right, because I simply did fk1 plus fc1 plus fk2 plus fc2, but they're actually going to the left, which is defined as the negative side for my coordinate system. I did the same thing over here. So let me write this down. Move this a little bit further down. And so what we have is, for the first equation, we have mx double dot 1 plus 2k x1 x1 plus minus k for x2 plus 2c for x dot sub 1 plus minus c for x dot sub 2 and that is equal to 0. Yep, that's about right. Okay. Second equation. Yeah, okay, so the second equation, we are going to get plus or minus k x1 plus 2k x2 plus, rather minus c x1 plus 3c x dot sub 2 is equal to 0. Now if we write this in matrix form, we get a mass matrix first, m 0 0 m, the acceleration vector, the damping matrix times the velocity vector, and then the stiffness matrix multiplied by the displacement vector is equal to this. And that's our first answer. Now that took a little bit over 10 minutes, and I'm just making sure that I didn't do any mistakes. Doesn't seem like it. Alright, so we're going to tackle the second one, and as you're going to see, you've probably already seen it before because I've talked about it in other videos. If not, you'll see that it's a lot faster. Okay, so number one, obviously we have 3 degrees of freedom because it would take us 3 fingers to stop the system. If I put a finger on all 3 masses, then the system is completely constrained. The mass matrix is m 0 0 0 to m 0 0 0 m. And so you see that the diagonal contains the value of the first, second, and third masses times the acceleration vector. Alright, no free body diagrams there. Plus, well, the damping matrix will only have a component for the first mass, and so here we'll get a C, and we'll get 0 and 0. The reason why we have zeros here is that there are no dampers between the first mass and the second mass for this guy, and there's no damper between the first mass and the third mass for this guy, so they're all equal to 0. Okay. And you get a big bunch of zeros for the rest. We're almost there. Alright, the stiffness matrix. In the diagonals, you're going to find the sum of all the stiffness values that are attached to that block. So the first element of the diagonal will be k plus k. That's 2k. The element to the right will be the stiffness value of the spring attaching mass 1 to mass 2. That's minus k. And since there are no springs attached between mass 1 and mass 3, you get 0. So we'll do the diagonals first. For the second mass, you have k plus k. It's 2k again. The third element of the diagonal, we have 2k here plus k. We have 3k. Let's go back to the second line. Now, are there any springs between mass 1 and mass 2? Yes. There's one, so it's always a minus value. It's minus k. You'll see a pattern here, symmetry. All right, the element between mass 2 and mass 3 is has a stiffness value. It's constant of minus k rather, but it's a minus because it's not on the diagonal. All right, I can already guess that here it's k because they actually represent the same value. So the third line is the third third mass, and the second column represents the second mass. So what's in between the third mass and the second mass? It's one spring, and since it's not on the diagonal, you put a minus value. Okay, minus k. So third line, first column, third element, and first element. Is there anything? The answer is no. And it actually completes our symmetry pattern. You see this, you see this. Okay. And we are done. So if I wasn't talking, it would have been a lot faster. Still didn't take us nearly as long as the first one. But we are done. It's less messy, and it actually feels good to do it that fast. If you want to have a PDF worksheet for this problem, I've posted it in the description below. As always, I thank you for watching.